Welcome everybody, good evening. Welcome back to our second to last speaker for this year's academic year. We have one more coming up on the first Tuesday of May. Tonight we have Professor Yongjun Yang, Professor of Mathematics, who is going to be talking about something that I don't know much at all about, so I'm looking forward to this. Prime numbers, past, present, and future. So without further ado, I'll turn the floor over to Professor Yang.
Thank you. First, I want to welcome you to our campus and welcome to my talk. As you can see, that I'm going to talk about prime numbers, and this is probably one of the oldest subjects in math. Right? The title is a kind of big one, but within 1 hour span, there's no way that I can cover all of the important things about prime numbers. So what I'm going to do is starting from the very beginning, okay, in the history of math, and how prime number, the study of prime number evolved, okay, and I will, along the way, bring you some important facts and interesting stories behind it. And hopefully, after 1 hour, you guys will find this kind of rewarding. So here we go. Math is a universal language of science. So to speak this language, you have to kind of understand the vocabulary. Okay? So that means you have to define stuff. Okay? You have to understand certain term, what it means. So definition. What is a prime number? A number is said to be prime if it is a positive integer greater than 1. So all those adjectives, positive, positive, negative, we know what that means. Integer is a kind of mathematical word that stands for whole numbers. Okay, you can think of it as whole number, no fraction, no decimal. Okay, and greater than 1. So whole number like 0 and 1 are not included. Okay, and so that means another set of conditions needs to be satisfied. It is divisible. So that's another term. By divisible, it means when the number is divided by something, the remainder is 0. There's no remainder. So for example, 7. 7 is divisible by 1. If you divide 7 by 1, you get 7 and no remainder. Okay? But 7 is not divisible by 2, because if you divide 7 by 2, you get 3 as the quotient, and then there's one little number remaining. Right? Are you guys with me? Yeah. Right? So the number has to be divisible by no positive integer other than 1 and itself. Well, that is because no matter what positive integer you have, it will always be divisible by 1 and itself. Take 7 as the example. 7 is divisible by 1. 7 divided 1 equals 7. And 7 is divisible by itself. 7 divided by 7 is 1. Right? So if you have such number that is only divisible by 1 and itself, it is a prime number. If it can be divisible by some other positive integers, then it is not prime, and that is called composite. Okay? Some pronounce it as composite. I mean, I've heard plenty of people calling both, so pick your preference. Right? So, a quick example, 7 is prime because 1 and 7 are its only positive integer factor. Okay, here another term here, factor. When two numbers multiply into a third number, then those two numbers can be set as factor of the third one. In other words, they are divisible, okay, or the third number is divisible by the first two. Okay, You can see another quick example. 6 is a composite number because why? Because 2 times 3 is 6. And why is called to be a composite? Because 2 times 3 is 6. Because 6 divided by 2 will be 3. 6 is divisible by 2. That means 6 is divisible by 1 and 6. And another one, 2 for sure, right? So 6 is not prime. Therefore, 6 is a composite number. Is that okay? Got it. Well, as you can see here, both definition of prime and composite has the condition that the number should be greater than 1. So how about this 1? In the history, actually, you will see, I will leave a remark here, but in the history, you will see this actually goes back and forth. Okay, there are some interesting story about it. So I'll leave it here. So whether 1 is considered to be prime or not. Of course, according to this definition, 1 is not prime, right? And it's not composite. Right? Okay. So, starting from the very beginning. Early history. Well, probably humans start the investigation of prime number. Oh.
I'm just coming closer.
Okay, I saw something's wrong. So, humans start the investigation of prime number from the very beginning after they start to count. Okay, one of the early evidence can be found in such Ishango bone. Okay, those are bones actually discovered in Africa, and they date back about 20,000 BC, and they have bones where lines are carved on the bone for counting purpose. Okay, on some of the bones that later discovered have prime numbers like 11, 13, 17, 19 on it. Okay, so those are the early evidence of prime number. Whether, many mathematicians believe that that's just a coincidence. How come these 4 prime number occurs at the same time on a bone? But anyway, that's evidence. Then, as you can see, about 1500 BC, evidence of prime numbers occurred in the so-called ringed mathematical papyrus. Papyrus is a kind of plant, okay, that grows near water and has broad leaf. So when it's dry, then you can write stuff on it. Okay, so that's something before paper is invented. And at that time, it was discovered a lot of mathematical calculations are written on this kind of papyrus. And when they do the so-called unit fraction, by unit fraction, a fraction with a 1 on the numerator, like 1 over 12. Okay, and it can be decomposed into, say, 1 over 16 plus 1 over 48. Well, you guys will have to believe me. You can check it, but I'm not going to do it now. Okay? So the decomposition of so-called unit fraction can be done much easier comparing with the unit fraction of prime number, like 1 over 7. That's actually much harder to do. Okay, so the early Egyptians did those unit fractions, and they discover unit fraction with a prime denominator are much harder. Okay, the real systematic study of prime numbers start from the ancient Greeks at about 500 to 300 BC. Okay, so they have the definition ready for the prime number, and then they have way to test whether a number is prime or not. Okay, so for example, the so-called trial division. So how do we tell whether 47 is prime or not? Well, if it's not prime, then 47 must be equal to some number times some number other than 1 and 47. So the smallest prime factor must be less than square root of 47, which is less than 7. So what you need to do is to test. The only 3 prime number before 7 is 2, 3, 5. So is 47 divisible by 2? No. Check. Is 47 divisible by 3? Well, I need a little bit of work. No. Check. And is 47 divisible by 5? No. Okay. 47 must be a prime. Okay? So that's the method called trial division. You try. All right? And using this idea, we have the so-called method of Sieve of Eratosthenes. You have a table of numbers where you can get rid of the composite from multiples of prime numbers, and then you will be able to count how many remaining numbers are prime within that table. Actually, if you look at that little handout that I gave you, well, by the way, this little handout I made can be trifolded into a little pamphlet. Okay, and the last page, as you can see, there's a grid, number grid, 10 by 10, 1 to 100. Okay, I have actually exercise problem for you. Okay, so from this little table, you can use the Sieve of Eratosthenes to come up with all the prime numbers. Okay, first of all, you take out 1. 1 is not prime by our definition. And then you take out all of the multiples of 2 other than 2 itself. 2 is a prime number because it's only divisible by 1 and 2. So 4, 6, 8, you cross them out until you get 100, which is a multiple of 2. Okay? That make sense? And then you cross out all of the multiple of 3 other than 3 itself. Things like 6, 9. Of course, 6 is already crossed out by multiple of 2. But anyway, if it's crossed out, then just leave it. All right? So 9, 12, 15, those numbers will be crossed out. And you go on with the next one, 5. And then you go on with 7, which is a prime number. And then do we need to cross out any other multiples? No more, because 100, the square root of 100 is 10. So if a 2-digit number is not prime or is composite, its smallest prime factor, smallest prime factor must be either 2 or 3 or 5 or 7. There's no other. Right? Okay, so leave the other. Well, it's not your homework, so if you find it fun, okay, you can work on that. And in fact, I have 2 other exercise problems. If we have the time, we can go through that little problem and use it as a little brain teaser. Okay? By the way, about primality of 1. So is 1 prime or not? Well, interestingly and strangely, at the very beginning, the early Greeks does not even consider 1 to be a number. They start from 2 for counting purposes, because 1 is 1. You have a stuff there. You don't need to count it. So that's the reason, actually, at the very beginning, 1 is not a prime number. It's not a number. Around 300 BC, Euclid come up with a very important series of books, okay, that called Element. The meaning of Greek element in Greek is letter. So in other words, the importance of element to mathematics is like letter to language. So really basic stuff in his point of view. It is the collection of all of the mathematical knowledge available to Euclid at that time. It's really a very brilliant piece of work that covers a lot of things that we take for granted right now. Right. And in his book, okay, the Elements has a series of 13 books. Okay, so in his book 7, he established the so-called fundamental theorem of arithmetic that says basically every positive integer can be written as a product of prime in essentially a unique way. So for example, I have a 24 there. 24 is 2 times 12. 12 is 2 times 6, so 2 times 2 times 6. And then go on, 2 times 2 times 2 times 3. Okay, so there are 2 prime number 2 factor and 1 prime number 3 factor. Of course, if you rearrange them in order, you could have different expressions. However, if you always go from the smallest to the biggest, that's the only way. There's no other way to factor 24. That's what I mean by the fundamental theorem of arithmetic. We have a 2 power 3 there that stands for the multiplication of 3 2 together. Okay, so 2 times 2 times 2 can be written as 2 with a little exponent 3. We call that exponent 3, just to make sure everyone knows what I mean. Another important result about prime number lies in his element book 9. And it basically says there are infinitely many prime numbers. So those prime numbers, I mean, as you can see from that little Sieve of Eratosthenes, more and more numbers are crossed out in the table, big table. So are there going to be enough spaces left so that the remaining number, prime number, is finite or infinite? The result is there are infinite many of them. And this proof is believed to be the so-called first documented proof by the method of contradiction. So what is this method of contradiction? I'll give an example. So for example, someone asks you to prove all trees need water. How do you prove it? How do you prove all trees need water? If you say, okay, this aspen tree needs water, that tree needs water, that tree needs water, if you pick 100 trees, they all need water, those are just evidences. Those are not really the proof of all trees need water. Right? On the other hand, your natural way of thinking is that, okay, if we cut off water supply to a tree, what will happen? It will die. Right? So if you assume the opposite of the result, then it is impossible. Something like that. There will be some kind of contradiction. And this is actually how the infinitude of prime number is proved. So we assume if there are only finitely many prime numbers. Okay, there are only finite. I don't care what that finite number is. It could be a million of them. It could be a billion of them. But it's finite. Okay. Then you think about a number that is the product of all those prime numbers. It's going to be big, but it's a number, right? And this number is going to be divisible by all prime numbers because it's a product, right? So now how about I add that number by 1? That's bad because the newly generated number is not going to be divisible by any given prime number we previously assumed, right? And that one is a new prime number. But that contradicts to the assumption we made that there are only finitely many of them. We already have them in the collection. This is actually a very logical proof, right? And this is the first document proof by this method. And then after that, Romans conquered Greece, and they preserved much of the knowledge of the Greek. However, not much progress after that. So after that time, until the 17th century, is called Dark Ages, the Dark Ages of prime number. Not much new thing occur. Okay. Yeah. So now, from the 17th century, well, starting from the 17th century, Europe, started to develop, and many mathematicians began to work on prime numbers. And one of the most important results is Fermat's little theorem. Well, it may look to be kind of abstract, but I'm going to explain. Okay, if P is prime, so symbolic language, if P is a prime number, and A is a number between 1 and P, okay, then A to the power of P minus 1. So P minus 1 will be a number, and this A multiply P minus 1 time, subtract 1, is always divisible by P. Okay, it looks to be very abstract language. But we'll see. I'm not going to prove it, of course. That will take time. But I'm going to explain some reasoning here. So what the most important application of this theorem is some primality test. You want to test some number to see whether it's prime or not. So for example, if 221 prime, well, you don't know. You can have trial division. But usually for large number, trial division is very slow. Okay, so we need some efficient method like this one. So we're going to pick P equal to 221, and then pick A to be 38. I just randomly pick some number, okay, and test. And then we see that, okay, A is the base there, and then we multiply this 38 220 times, right, that's P minus 1 time, to get a number, and then subtract 1. Well, it's going to be a big number. Okay, but it turns out this number is divisible by 221. What does that say? Is 21 prime? We don't know. Basically, it means this is a sufficient condition. If A is true, then B is true. You cannot say it backwards. If B is true, then A is true, right? So what it says is actually just saying that, okay, we observe B is true. But that doesn't tell you anything about whether A is true or not. However, if we try again, pick P to be 221 once again, and let A to be 24, another test. And then, okay, A is 24, repeated 220 times again, minus 1. And then you see that number is not divisible by 1. What does that say? Then 221 cannot be prime. Because if it's prime, then for any A between 1 and 221, that operation will give you something that is divisible by P. But this one is not. So the logic is this. If A is true, then B is true. So if B is false, you can safely say A must be false. Right? That's the logic behind it. If B is false, then A cannot be true, because if A is true, B would be true. right? So actually, we give names to these kinds of numbers. The 38 is actually called a Fermat liar for 221 because it actually lies about the information on 221. However, 24 is said to be a Fermat witness because it actually proves 221 is not prime. Is that okay?
Yep.
Okay, so those are interesting names. The liar, the Fermat liar, is give you the same result as the theorem, but it actually covers that 221 is not, in fact, not prime. Okay? The proof of this Fermat's little theorem can be, done in many different ways. And one of the most elementary proof is by counting necklaces. Okay? I can only give a quick description here. So what you do is that you count a string of p bits, so whatever this number is, p bits, and then using 8 different colors. So for example, if you have 2 colors, black and white, all right? And then you make a necklace, okay, so make it a circle. How many different styles are they? And using this elementary phenomenon, you can actually prove this Fermat's little theorem. Okay? If you guys are interested in it, you can actually look for the information online. It's everywhere. It will, if actually I'm going to prove it here, it will take at least an hour. Right? But you can see that these different series of, subject of math can be actually related to other things, like combination. And the Fermat's little theorem is later generalized by Euler into Euler's Toten function and Euler's Toten theorem. Okay, and the Fermat's theorem and Euler's theorem really lays the foundation of modern analytic study of prime number. Okay, so after this time, we have much better tools rather than at the beginning of time we just do those multiplication and division. Okay. All right. Well, during the long course of study of any subject, how the results are developed. In math, it's especially true that they are developed through conjecture. So people or mathematicians study different patterns, and then they make assumption whether certain statement is true or false. Okay, so make assumption or a statement. We conject that this might be true, and then you try to either prove it or you try to disprove it by looking for counterexample. So, for example, Fermat made a very famous conjecture about a primarity of such kind of number. So it's 2 to the 2 to some power n plus 1. And at that time, he can only investigate the case of n equals 0, 1, 2, 3, 4. After that, the number gets too big for that time to be calculated, then he could not verify anymore. And it turns out for n equals 0, 1, 2, 3, 4, the so-called Fermat number are all prime. So he made a conjecture. Such numbers are all prime numbers. Well, all those conjectures do not necessarily mean they are always true. In fact, unfortunately, for the very next one, n equals 5, Euler, another famous mathematician, later, after about 100 years, later proved it's not prime. Unfortunately. But it still doesn't matter. We still have this kind of number named after Fermat. It's called Fermat's number. And in fact, the question still remains open. Are there any other prime Fermat number after n equals 4. We've checked n equals 5, not prime, n equals 6, not prime, n equals all of the numbers so far we've checked, they are all composite number. However, that is not a proof, not a mathematical proof that all Feldman number after n equals 4 is composite. Unless you give a proof, a complete mathematical reasoning, you cannot claim. So it is still remain as an open question. The next one is Merson's conjecture. Merson is a monk, actually. I guess at that time they have enough time to pursue his own interests. Okay, so he especially investigate the prime number of 2 to the power of p minus 1 form, where p itself is a prime number. So for example, 2 squared, that's 4 minus 1, 3. 3 is a prime. Or say 2 to the power of 5. 5 is a prime number. That's 32 minus 1, 31 is prime. Okay? Of course, there's no guarantee that all of these are prime. In fact, 2 to the 11 minus 1 is not prime. However, he studied this kind of prime number, and later it's called Merson number. For Merson number, he made an original conjecture saying that before p equal to, I think, 257, there are 11 of them prime, and all the rest are composite. Well, after another 100 years, it was developed that there are 5 mistakes. 3 more should be included as prime number, and 2 of them he gave was actually not prime. But it still doesn't matter. This kind of number is still named after him, and this number actually occurs quite a bit, okay, at a later time. Okay, this is called Merson conjecture or Merson number. The later 2 are the 2 of the long-standing conjecture that are still open. One of them is the Goldbar conjecture that says every even integer greater than 2 can be expressed as the sum of 2 prime. So for example, you start from 4. 4 is 2 plus 2. 6, 3 plus 3. 8, 3 plus 5, and so on. And you check all of those numbers, even numbers more than 2, and they always can be expressed as sum of 2 prime. But that's not a proof. This is still a standing conjecture. Although we have no counterexample showing this statement is not true, but there's no proof that this is true. In fact, the best result so far is the following. So bear with me. It's developed in 1970s sometime, and by a Chinese mathematician, Chen Jingren. And the result is this. For a sufficiently big even number, it can be expressed as the sum of 1 prime number and a product of 2 prime numbers. We call that 1 plus 2. So 1 plus 2 is solved, but not 1 plus 1 yet. Many mathematicians devote their entire life just to try to solve this kind of thing. The twin prime conjecture. There are infinitely many twin prime. By twin prime, a prime number that differ only by 2. So for example, 3 and 5, 11 and 13, okay, those kind of things. Again, you can find many, many of them, but we do not know whether, in fact, there are infinitely many pair of twin prime. Still remains an open question. However, the best result, now I'm going to say the best result was there was a breakthrough in 2013 by a lecturer in the math department of University of New Hampshire, another Chinese immigrant. So he comes to the United States at some time ago. So he proved, a breakthrough that says we can show that there are infinitely many pair of primes with a fixed difference to be less than 70 million. So prime 1, prime 2 has a difference of some number between 70 million. And there will be another pair. And there will be another pair. And we can show there are infinitely many such pairs. Although it's still very different from this original statement, but it's still considered to be a breakthrough. In fact, that bound of 70 million is now lower to 246 as of last year. Hopefully, one day we can prove that that bound is to be shrunk to 2, then the problem is solved. So you can see the progress is not made usually in stride. You make baby steps, okay? But hopefully there will be a breakthrough. At least we now know there's a bound. Originally there's no bound. That's a breakthrough. Okay, I gotta pick up my pace a little bit. Okay, speaking of the Merson number, there's a very interesting story about this Merson number M67. By M67 is 2 to the power of 67 minus 1. Remember the Merson number that I mentioned in the previous slide. Okay? So originally, Merson conjectured that this is the prime number. However, in 1876, mathematician Lucas demonstrated that it must have factors. In other words, it cannot be prime. It's a composite number. But at that time, he could not prove or find what kind of factor this M67 had. So in 1903, American mathematician Franco, I believe, yeah, Frank is his first name, gave a very famous all-silent lecture, so-called lecture, in American Mathematics Society meeting. And after he's introduced to the audience, then what he does is that divide the board into 2 parts. On one part, the left part, he did this 2 to the 67 power minus 1. Of course, you have to multiply 2 67 times. That's not going to be easy, right? It will generate a huge number. Okay, so on one side of the board. Then on the other side of the board, he did the hand calculation of 193,707,721 times that bunch. And turns out, after 1 hour, they're the same. And after that, he returned to his seat. So the entire 1 hour, he didn't even utter one single word. And that's it. And of course, this received standing ovation from the audience. It's basically just a proof that he found the factor, prime factors of that M67. Okay. Well, so those baby steps about prime number here and there, and eventually come up with some very nice results about the so-called prime number theorem. Although the prime numbers are like weeds in the grass, they come everywhere, and with seemingly no pattern at all. Actually, we do have pattern. Okay, so the prime number theorem basically gives the distribution of prime numbers in such a way. If pi of n, so say this pi is a symbol, for any given number n is the number of prime before that n, or no greater than n. So for example, pi of 10. What's pi of 10? The number of prime before 10. 2, 3, 5, 7, 4. So pi of 10 equals 4. So it basically gives you how many prime are there no greater than this number n. And it turns out that this pi of n is approximately n over natural log. This ln stands for natural logarithm of 10. And logarithm basically tells you how big this number is, how many digits are there. So roughly speaking, the probability of a randomly chosen integer with n digits, okay, or no more than n digits, is prime, is very close to the reciprocal of logarithm of n. In other words, the number of digits. So 1,000 digit number and a 2,000 digit number. The 2,000 digit number is half as likely to be a prime comparing with a 1,000 digit number. Okay? And this little table there basically shows that the difference in terms of ratio, the relative difference between pi of n and that n over ln of n is roughly 1. In fact, you can see from this little table there are much better approximations later on using another calculus concept of integration. But anyway, okay, you know mathematicians are working hard, really try to get better and better results. Okay, so these are some newer results about prime number. And okay, the next one, although we know there are infinitely many prime numbers, but it never stopped people or mathematicians to look for the largest known prime. M31, that's Merson prime, 2 to the power of 31 minus 1, turns out to be a 10-digit number, and that was discovered in 1772. The record stood for about 100 years. And then, I mean, there are of course others. The next one I believe is Euler's prime, and that's M of 127, another Merson prime. But anyway, before and after the computer, there's of course a huge difference. So at 1951, this number, 2 to the power of 148 plus 1 divided by 17, whatever it is, okay, it is a 44-digit number, and that is the largest prime not set by a computer. Actually, within the same year, when computers used, the record jumps to 79 digits. Humans are no competition of prime number in terms of this huge calculation. And then after that, I mean, there's a huge table of records of largest known prime. So the 1989, this number, which has 65,000 some digits, is the last record that is not a Merson number, not a Merson prime. And after that, you see Merson prime evolve kind of constantly in the record table. And right now, I think this number was developed, in 2016, and that is a Merson number with 22 million more digits. So just how big this number is, to give you guys a little bit of idea. So just say if you, read this number, by read, not glance through it, so you speak out loud. So 1, 2, 3, 4. Let's say you say 3 digits in 1 second. And just do this again. Of course, you have to sleep and rest. And so let's say you do it like a work 8 hours a day. And how long will it take to just read the entire number? You have to use a whole year just to read this number. And only the supercomputers can do it. There's no way our human can do it by hand calculation. In fact, you can see a little bit of table that basically give the year against the size of the largest known prime. So right now we are at about 10 to the 7th, okay? 7th power of 10, that many digits. So when will we see a prime with a billion digits? From this table, it shouldn't take too long. A billion digit means 10 to the power of 9, so that just means another grid above. Okay, within maybe 10 years, 20 years, we should get there. Okay, well, enough of these abstract stuff. So maybe we should think about some application. Why do we want to study prime number? Are they any useful at all? Of course, theoretically, any study of prime number or other stuff are useful. Usually, the quest for knowledge is not just linear or one-dimensional. So you want to cover some of the unknown area, you have to go enough to be able to know things about the unknown region, right? Just by theoretically, there is a need to study prime number. The theory of prime number can be applied to other subjects of math. But that's not what I'm going to talk about. Okay? 3 little applications. Cryptology. Nowadays we do this online purchases all the time. So one little question, how do you guarantee security of information like credit cards, bank accounts, personal information? They cannot be transmitted publicly or openly, right? Therefore, you have to code it. So how is this done? The coding cannot be done too hard because we as end users should have access to it, right? But we should not be able to decode other people's information, right? So what they do is this. They use a public key that is a so-called semi-prime. It is a product of 2 large prime numbers. And by large, I'm speaking about hundreds of digits. So hundreds of digits of prime number 1 times hundreds of digits of prime number 2. Those 2 prime numbers are private keys where your credit card company or whatever the sales, they know. They can use it to decode the information. But what we have is a public key that's the product of these 2. We can use that to transmit our information. Unless the hackers have really super powerful way to decode, to decompose the semi-prime into those 2 private keys, there's no way they can actually decode it. Does that kind of make sense? Private keys combines into a public key. We have the public key, but there's no way we can break it into 2 private keys to decode the actual information.
Unless we're highly skilled mathematicians.
What's that?
Unless we're really skilled mathematicians.
Right.
Okay.
Random number generator. So in real world, we also need to study chance behavior. So flip a coin, head or tail, or other random behavior. If you want to pick out a random sample, how do you do it? You cannot have a bunch of people there just to flip the coin for you and to tell whether I should choose this one or that one. So there must be some kind of generator. And all those generators will come from computer. There must be some kind of algorithm behind it. So since it's an algorithm, then it cannot be totally random, right? It has to study, okay, step 1 you do this, step 2 you do that, step 3 you do that. There's no way, although you have a function called the random number generator, but where is that number come from? That's still from some algorithm. Well, actually, is pseudo-random in the sense that the random number generator you see from all of the computer language are actually the remainders of multiples of one large prime divided by another large prime. So you take a large prime, the multiple of it, divide another large prime, the remainder will occur almost randomly. That's how they actually generate random number. And primes in nature, I have a little picture here of cicadas. Cicada is a very interesting kind of bug, and they spend most of their life underground, and then sometime they will come out and hatch and breed and reproduce, and then babies will go underground, stay a lot of time. So this is a life cycle. And it turns out that when they do such kind of observation, the life cycle always have period of 13 or 17 years, which are interestingly prime numbers. How come? Well, just think about their predators. If the period of cicada is 12, say 12, composite number, then the predators will have chance, if their life cycle is 2 years, 3 years, 4 years, 6 years, suppose they all start at the same time, will have a chance at 12 years to catch those cicada. Where if the period of cicada is 13 or 17 years, unless the predators all have the life cycle of 1 or 13 years, there's no way they can catch them, right? So those little bugs actually know prime number. Well, of course, it may come from a natural selection. So those actually have a composite year as period. Well, this thing goes this thing. So even they know, so we should know, right? We should know about prime numbers. Okay, I think that's all of it. Okay, the rest is just a couple of problems as brain teasers. So I'll ask to see if you have any questions. Yeah.
So, what is the name for 1 then, if it's not composite or prime?
Oh, yeah. Well, I got too excited and forgot about this story. Yes, at the very beginning, as you see, 1 is not prime, or not even considered as a number. Okay? And then mathematician really grows very nervous about leaving this 1 out after they set up 1 as a number. So some mathematicians actually include 1 as a prime number. It actually has lists of prime number up to certain digits, and this kind of book published as late as 1950. Some mathematicians still think 1 is the prime number. But of course, if you include 1 as a prime number, a lot of results will have to be restated. For example, the fundamental theorem of arithmetic, like 15. 15 is 3 times 5. That's the only factorization, right? But if you include 1 as a prime number, then it can be written as 1 times 3 times 5. So you have 2 of them. So it's always kind of a debate during some time, 1 should be prime or not. And then as things turn, more and more mathematicians get comfortable leaving 1 out and just say 1 is a unit. Okay. Let's leave it out of the discussion of prime number or composite number. So 1 standalone as its own class is a unit. And then after 1, we have prime and composite number. Okay. And I believe early 20th century, some mathematician, I forgot his name, is believed to be the last famous mathematician who still think 1 as a prime number. After that, almost nobody says 1 is a prime number anymore.
So today, nobody really would call it a prime number. Today, nobody would really call it.
Right, but of course, everyone is entitled to his own opinions as long as you establish a system that other people can accept. I have no question about it. Anything else? Other question? Well, if you find those brain teaser problem interesting and you want to discuss with me, you're more than welcome to do so.
I do have a question. It's kind of a personal one. But what led you to your interest in prime numbers?
Actually, the number series is not my primary interest of research. However, I do like to have those kind of interesting problems. As probably some of you know, I ran math club for high school and middle school students. So they always have this kind of nice, interesting questions that involve prime numbers or other kind of short, compact, like those brain teaser problems that I gave you. And this brings me to the interest of investigating the fact of prime number. You can, I mean, I can treat it as a hobby. Think about it. Good brain teaser. Okay.
I was wondering about that silent lecture. So that man did that before there were computers or anything like that. What sort of things could he use to find those factors?
The what?
The Mr. Cole that factored out that.
So
he did that in 1903 or something like that?
Yeah, it's 1903.
So then he didn't have a computer or anything to do that.
Oh, yeah. A side story. So he later admit, how did he actually do that? He used Sundays, all Sundays of past 3 years to check by hand calculation. Yes, I can answer that. I think I read it somewhere. Yeah, all 3 Sundays of the previous 3 years. Oh, I mean, all the Sundays of previous 3 years. He's just determined to do it. I mean, it's unimaginable.
Yeah, that's just
Yeah. Anything else?
All right. Well, thank you, everybody, for coming. Thank you.
Very good. Thank you.